Okay, so let's wrap up this first section with two proportions. We have looked at the sampling distribution for the difference of two proportions. We've looked at confidence intervals to estimate the true difference of proportions. Now we're going to look at significance testing for the difference of proportions. An observed difference between two sample proportions can reflect an actual difference in the parameters, or there is a chance that it may just be due to chance variation in random sampling or random assignment if it's an experiment. Now, significance tests help us decide which explanation will make more sense. When you're writing your null hypothesis, it's going to have this general form. We are saying that the two proportions are equal, meaning that the difference between the two will equal 0. Okay, so if you're thinking about a number, it's 0. The alternative hypothesis says what kind of difference we expect. If we expect the first proportion to be greater than the second proportion, the difference would be greater than 0. If we expect the first proportion to be less than the second proportion, we would get a difference of less than 0, right? A big number being subtracted from a smaller number leads us to a negative number. Or we can just say that there is a difference, meaning that when you subtract it, it's not 0. I don't have a preference which way you write your hypotheses. Just realize that it can be either or. So here's a good little visual. If we are thinking that it's a positive difference, we're probably looking at a positive z over on this side of the table on the right tail. If the difference is negative, we probably are looking for the left tail, and a not equal to is on both tails, and we're used to that from before. So, assuming that our conditions have been met, the random, normal, and the independent. So remember, same way that we tested before, data is produced from a random sample from each of the populations, or it was a randomized experiment. You have to check 4 things for normal, right? Make sure they're all at least 10. You are going to be using p-hat here. That's different than what we did when it was just one proportion. Then we would use the claim. Since our claim now is just 0, that doesn't make any sense. So we're going to be using the p-hats. Independent, both samples have to come from independent observations, and then check the 10% condition for each of your samples. To test the hypothesis of H sub O is that the difference is equal to 0, you have to find, now this is new, you have to find what's called the pooled proportion p-hat sub C. Okay, C stands for combined here. It's the successes in both samples combined. Then you're going to use that in your denominator. So this is different. Now, how do you get the combined proportion? Well, you just combine them, right? Add your 2 x values, add your 2 sample sizes, and that will be your proportion used down here. This is not on your formula sheet, but it's easier to remember because it looks a lot like what we used in confidence intervals. It's just using P sub C here. The one on your formula sheet is a little bit different, and it doesn't say sub C, but it is what that is supposed to be. Now, why do we pool? So a little bit of background. We have merged the data from the 2 samples to obtain what is called the pooled estimate of the standard deviation. We have done this not because it is more convenient, because it isn't, right? There's more calculation involved, nor because it reduces the measurement of the variability. It doesn't always, right? Often the pooled estimate is larger, but because, and here's the kicker, it gives us the best estimate of the variability of the difference under our null hypothesis that the 2 sample proportions came from populations with the same proportion. If you need to pause that and read that to yourself, I understand. If you want some more details about it, you can go to this link here, and this will be on the PowerPoint online, so you can go there. Okay, let's go through an example together. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005-2006, 19.5% showed some hearing loss. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? So first thing we want to do is we want to state our hypotheses and define any parameters. Because there's a difference in proportions here that we're looking at, there's going to be 2 parameters that we define. I'm just using sub 1 and sub 2. If you wanted to use something different, that's fine. So I'm going to say that P sub 1 is the proportion of all teenagers with hearing loss in 2005-2006. And then P sub 2 would be the proportion of all teenagers with hearing loss in 1988 to 1994. Okay? So, my hypotheses, I want to know, is there a difference between the two? And I want to know, has it increased? Has the proportion of all teens with hearing loss increased? So that's why I was specific here. Instead of just saying all teenagers, it's teenagers with hearing loss, okay? Because that's what I'm trying to estimate. So if I want to say if it's increased, if P1 is my most recent year and P2 is the one before that, that means P1 would be greater, and that's why I'm saying this difference is greater than 0. Now, what test should we use? Let's check our conditions. The name of the test, so this would be like the plan step, if you will. This is going to be a 2-sample z-test for the difference of proportions, right? P1 minus P2. We have our 3 conditions to check. First condition is random. The data did come from separate random samples, so that's important. Next comes our normal condition. I have 4 things to check. So N1 and P1, or P-hat1 I should say, come from the 2005-2006 data. So 1800 was that N sub 1. 19.5 or 0.195 was that P-hat. Both of those are bigger than 10. N2 P-hat2 comes from 88 to 94. N was 3000 there. P-hat was 15%. All of those were at least 10, so we're good to go with normal. Lastly, for independent, my samples were taken independently, and there were at least 18,000 teenagers in the year 2005-2006, and also at least 30,000 teenagers in 88 to 94. So my conditions have all been met here. Now, we want to calculate the pooled sample proportion, right? We want to calculate the pooled sample proportion. So this is the formula that we're going to use to calculate our pooled sample proportion. Now, they didn't give us these values, 351 and 450, but I can find them from right here, right? There's that proportion, my X there, and here's my X here, 351 and 450. So, and then my sample sizes were here. So my pooled proportion, my combined proportion, is going to be 0.167. Okay? So now let's go ahead and calculate the z-score and determine the outcome of the significance test at our 0.05 level. So here's the formula that we're going to use. So we plug in everything that we have, and we end up getting a z-test statistic of 4.05. Now we need to get our p-value from that. Now because this was a greater than in our alternative, I want to find the probability that my test statistic is greater than 4.05, excuse me. And that's going to be really, really, really small, right? That's not even on our table. So it's about 0. It's about 0. Now, what does that mean? Well, since our p-value is less than our alpha of 0.05, we're going to reject our null, which means we do have convincing evidence that the proportions of all teens with hearing loss has in fact increased from those 2 time periods, from one to the next. All right, now let's see what else we can think about this. Between those 2 studies, Apple happened to introduce the iPod. If the results of the test are statistically significant, which they were, can we blame iPods for the increased hearing loss in teenagers? Can we blame the iPods? As much as we might want to, we cannot, right? We didn't do an experiment. We didn't assign some teens to listen to iPods and other teens to avoid listening to iPods, so we can't say that iPods are the cause, right? Correlation does not mean causation. It is possible that teens who listen to iPods are also likely to listen to music in their cars, and then perhaps car stereos are causing the hearing loss. So I can't say that iPods caused it. This wasn't an experiment. This was just an observational study. If you were to do this in your calculator, as far as the do step, which I would encourage you to do, You would go to tests and you would choose option 6 on most calculators, which is for two proportion z-test, and that will help you out so you can check your math, because sometimes when we're doing this we forget about the pooled, because this is the only time we're going to be using this pooled combined proportion. It's only in significance testing for proportions. Now the next example I want you to try on your own. Okay, it is a full-on 4-step process for significance testing for the difference of proportions. Okay, so try that out, and then the next video is going to walk you through that solution.